All right, let's continue with part B. We have the exact same trig substitution, x equals 4 sine theta. And for that reason, I just copied down the right triangle setup here. As I mentioned earlier, you can change the setup the way you want. You can place the theta to the top corner over there, but you have to realign all these quantities here. Okay, so let's quickly go through this substitution by taking the derivative of x, differential of x, looking at the differential of x, which is the derivative of 4 sine theta times d theta. So that's 4 cosine theta d theta. Okay, and here 16 minus x squared, I'm going to replace that in the description here. I'm going to sort of like rewrite that here by using this triangle, or you can use the Pythagorean theorem. So cosine theta here in the triangle is adjacent divided by hypotenuse. Okay, adjacent is 16 minus x squared in square root divided by 4. That's the hypotenuse, right? I'm going to go ahead and write this down here. Okay, that's good. And if I multiply both sides by 4, let me just rewrite here. 4 cosine theta equals 16 minus x squared. And that's radical 16 minus x squared. Okay. All right, so let's rewrite this integral in terms of only theta. Okay, let's put a border here. All right, good. So x squared is going to be 16 sine squared theta divided by radical 16 minus x squared, which is found as like 4 cosine theta. And dx as well is cosine, 4 cosine theta d theta. All right, let's cancel out 4 cosine theta by this 4 cosine theta. Okay, so then I have the integral equal to 16 sine squared theta d theta. And this is the topic of the previous section, that this is an integral involving the powers of sine and cosine, but in this case it's just sine. So sine raised to the power of 2. And one of the items listed over there was telling us that if you have even powers of sine or cosine in the integral, you may try using the power reducing formulas. So let me just remind you what that is. All right, here are the power reducing formulas, one for sine, one for cosine. So we're going to use the version that involves sine. So 1 minus cosine 2x over 2. Let's go back here. 16. 1 minus cosine 2x over 2. But we have to go with theta because we don't have any x here in this formulation. This is the theta formulation, right? All right. So let's simplify this further. So this is equal to 8 d theta minus 8 cosine 2 theta d theta. Okay? So the first integral is relatively easier. Let me just continue from here. This is 8 times theta. And cosine 2 theta, you can use the u substitution if you want to, but that is integrated as sine 2 theta divided by 2. So that's 4 sine 2 theta plus c. Okay? So now we're not done, right? Because we have to rewrite this expression in x. So we have to back substitute theta. Okay? And we should get the x description of this. Let me just go to a newer slide and I'll explain it there. All right, so I just rewrote this quantity. So I need theta and sine 2 theta. This is a double angle, so we should probably use the double angle formula. Go ahead and check the double angle formula from trig for sine. So this is 8 theta minus 4 2 sine theta cosine theta plus c. So in other words, it's 8 theta minus 8 sine theta cosine theta. And remember that we had the substitution for sine theta, x equals 4 sine theta. In other words, this is x over 4 equals sine theta. Okay? So here I need the exact expression of theta, and that's where we rely on to the inverse trig functions. So if sine theta equals x over 4, then I can sort of like grab theta as sine inverse x over 4, or in other words, arc sine x over 4. Okay? So keeping that in mind, let's just do the final conversion here. 8 times sine inverse x over 4, or again, arc sine x over 4, whichever the notation you want to call it, minus 8 times sine theta is already x over 4, right? And now I need cosine theta, and cosine theta can be read out of the right triangle. That's the adjacent divided by hypotenuse. Okay, so I'm going to write adjacent divided by hypotenuse plus c. Okay. So you can go ahead and simplify this more, but that's pretty much what the final output looks like for this integral. Okay. So to sum up, we had square root of difference of squares. The first one is a number squared, and the other one is the variable squared. So this, by the way, the position of the number and x's here is very important. Okay, so this is again 16 minus x squared. So first one is number, the other one, the next one is x squared. So in other words, this is 4 squared minus x squared. But if you switch the order, if you write this as like x squared minus 4 squared, that's a totally different deal, and then this substitution will not work, and this could be one of those homework or exercise problems. And I may probably mention that in the other videos. But I think we're done with this example, and we were able to get rid of the square root terms in both integrals by using this trig substitution. And the resulting integrals in both cases were much easier than these two integrals, the original integrals. All right, so I'm going to end this video, and thanks for watching. If you have any questions or comments, please send those to my way. Bye.